So we're in section 11.5, part 2. So since the school moved to Google, all the teachers have automatically got a Google Plus account, and then because all of my videos are on YouTube, I have a separate Google Plus account for my videos. So when I find my website by Googling Mr. Beamer because it's the first one that comes up, which is kind of nice. But in the Google Images, pictures of these screenshots show up all over in Google Images for Mr. Beamer. So I've been meaning to show you this little thing for a little bit, but this is kind of a nice little I guess a proof using the dot product. So I want to do this, and it doesn't require much. So I'm going to draw a couple of vectors here. And we're going to call this one A, and this one B, and this angle alpha, and this angle beta. Was that your elbow? And we're going to say that the magnitude of A and the magnitude of B are both 1. So one expression for the dot product, we can say that A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. So that just gives us the cosine of alpha plus beta, because the magnitudes of each are 1. And then our components, we'll write another expression for the dot product. So the components of A is the magnitude of A times cosine alpha I plus the magnitude of A times the sine of beta j. And B is cosine beta I minus sine beta j. So we're going down negative y direction here. So A dot B, we said, is the cosine of alpha plus beta. And if we form the dot product with our components, and does this nice little thing look familiar? This is our identity for the cosine of the sum of two angles from the dot product. And if we drew our angles, if we drew our vectors this way, so if we drew them like so, our two vectors, so that both were in the positive direction, and that were alpha, and that angle were beta, not beta, there we go. And we could go through the same procedure and find and come up with the identity for the cosine of the difference of two angles. So the angle between the two vectors would be, for this one, it would be beta minus alpha, the way I drew it. But we get the identity for the difference, the cosine of the difference of two angles.
Mr. Beamer, for vector A, is it sine of beta or alpha?
Oh, this should be alpha. You're right, thank you.
That was confusing.
Because then I wrote alpha down here, didn't I? Yeah. And we could do the same thing by forming the cross product of two unit vectors and get the sum and difference formula for the sine of the angle, the sum of an angle or a difference of the angle. Going through the same process but forming the cross product of A and B. So I just thought that's a nice little connection between vectors and trig identities. Kind of nice. All right, planes. So we used, for lines last time, we used a point and a parallel vector. For a plane, we're going to use a point and a normal vector. So let's get ready to talk about planes. Let me draw a picture here. We'll draw a plane. So here's my plane. And here's a point on the plane. And here's a normal vector. We're going to draw a normal vector here. So there's a vector normal to the plane. We'll call that N. And I'm going to put a point in the plane, another point Q. And we'll draw the vector PQ in the plane. So there's our vector PQ. And our N is normal to PQ. Normal to the plane, so that's a 90-degree angle. So our plane contains the point P. And we'll call that P, we'll call that x1, y1, z1. So we're given some point in the plane. And our normal vector N, we'll just call it A, B, C. We're going to define a plane in space as the set of all points Q such that this vector PQ is orthogonal to N. So any point we pick that's on this plane, if I draw a vector from our given point to that point Q, that vector PQ is going to be normal to N. That's how we're going to define our plane in space. So because PQ and N are orthogonal, we can say N dot PQ equals what? 0. This is the vector equation of a plane in space. So we're given some point P. N dot PQ equals 0 is the vector equation of a plane. So our plane will have some normal vector, we'll have some point that's on our plane, and this gives us our equation. And then to make this more useful, what we're going to normally calculate with, we're going to use to actually do things, we're going to write out the components of this dot product and work with that. So I'm going to switch pages and then we'll write out that dot product. So we're going to say that N, our normal vector ABC, dot and PQ, our vector PQ, is going to be x minus x1 for my x component, y minus y1 for the y component, and z minus z1 for the z component. So our point Q is just some arbitrary point x, y, z. And x1, y1, z1 is our point P that we're given on our plane. and this dot product equals 0. Write out this dot product, I get a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. This is our standard form for the equation of a plane. And this is, in a large part, this is the form of the equation that we're going to work with the most. Our normal vector is given by these components, our point on our plane, x1, y1, z1. Just to reiterate, a, b, c is our normal vector, and our point x1, y1, z1 is in the plane. So that's our standard form. If I distribute here and regroup terms, I can write ax plus by plus cz plus d equals 0. So I distribute the a, the b, the c, and the d term contains all the portions involving x1, y1, z1. And this is called the general form. This is our general form. And we'll see our equation of a plane written in this form as well. So this is our general form. And note from the general form, our normal vector comes from the coefficients on x, y, and z. So we can always, no matter how what form our equation is written in, we can pick out our normal vector very easily. So this gives us a nice, clean way to represent and work with planes in space. We use a normal vector and we use a point on the plane. So questions on our definition, on our development here. We will hopefully become very familiar with normal vectors and planes. We'll work with them quite a bit in second semester. All right, so let's look at an easy example working with the equation of a plane, and then we'll talk a little bit more about how we're going to, a couple of different ways that we're going to work with them. So we want our equation of a plane. And this one is a very easy example, a very gentle example here. Plane containing, gentle, yes, it's a gentle example. Negative 3, 0, 7. And our normal vector n equals 5i plus 2j minus k. So to write our equation, the normal vector gives us our coefficients, and this is our x1, y1, z1. So all we have to do is write out 5 times x minus negative 3 plus 2 times y minus 0 minus 1 times z minus 7. And that equals 0. If I distribute, I can write, I'm just going to distribute here, 5x, write out the steps, plus 2y minus z plus 7 equals 0. Collect these terms, I get 5x 13 because I wrote a 1 and then the 3. This is a special property of planes in space. Minus z, and this should be not a z but a 7, equals negative 21. So this would be our standard form and our general form. All right, so that one not too bad, other than my multiplication skills. What's that? Is it 22? 13, 20, yeah, 22. It's a rough day for arithmetic here. All right, 22. Good thing that it's almost Thanksgiving. Okay. It's like I have a discussion with my wife fairly regularly that arithmetic and math are different things. So if we could do all of this without numbers, it would be so much better. If this was just ax minus b plus cy minus d z minus f, and then we could just do it that way. It'd be so much nicer. All right. So one important property of planes, geometric property. Any questions other than why I couldn't do arithmetic there? Important property of planes is if we have two distinct planes in space, they are either going to they're either going to be parallel or they intersect in a line. And often we're interested in what is the angle between the planes if they intersect in a line. What's the angle formed by the two planes? So we can show that the angle between the planes is the same as the angle between their normal vectors. And I'm just going to say they're normals. So let me see if I can draw a decent picture here that's not too confusing. So here's our plane that's tilted at an angle. And our normal vector to this plane, I'll do that in black. So and I'm going to call that N1, and this is the little place where it intersects the plane on that little X, and then I'll do the other plane underneath here in dotted red. So there's my other plane underneath here, not too bad. And here's the angle that we're talking about, this angle theta. And let me draw the normal vector to the other plane. I'll do that in dotted red also. And I want to do it right up through here. so. And there's the little place where it's intersecting the plane down there. And we'll call that N2. So what we just said is that this angle here is the same as that angle there, between their two normal vectors. So we can find the angle between the two planes. I'm going to say that the cosine of theta, what's going to give us the cosine of theta here? If we have these two normal vectors. So our dot product, our friend the dot product. Our cosine is going to be the n1 dot n2 divided by the magnitude of n1 times the magnitude of n2. And I use the magnitudes or the absolute value of the dot product because we're talking about an acute angle. We're talking about an acute angle between the planes. Magnitude, absolute value. So the dot product is a scalar, so the bars mean absolute value. When we're talking about a vector, I guess I could put the double bars down here for our magnitude. So we're talking about an acute angle, so we take the absolute value of the dot product. So we're not interested in the sign of the dot product. We just want an acute angle. So what would it tell us if n1 dot n2 equals 0? The same plane? They intersect at a 90-degree angle. So we're going to say the planes are perpendicular. And if n1 equals some scalar multiple of n2, what do we know about the planes? They are parallel. And if we formed our dot product, what would happen with our dot product? If we're thinking about how could we think about the angle between two parallel planes? 0 or 180, right? So what's our dot product going to be? 1 or negative 1, right? So our angle would be 0 or 180. So that couple of ways to tell if our planes are parallel. So the dot product turns out to be a nice little tool that we can use for a lot of things. So this is how we can figure out the angle between two planes. Well, there's another thing we can use a dot product for. Often we're interested in the distance from a point to a plane. So let's draw a picture for this, and we will come up with a way to find the distance from a point to a plane. So here's our plane. And here's our point in the plane P. And we're interested in the distance of the plane to this point Q. So here's my normal vector. With our plane, we're always interested in this normal vector. That gives us a lot of information about our plane. So there's n. And I'm going to now draw a vector from P to Q. and we're interested in this distance. And we have a nice right triangle there. So we're interested in D, the length of this side. Well, here's what I'm going to do to find D. I'm going to project this over this way as well. And this is D. And I'm going to call this angle. Let me move N up here a little bit. That angle theta. So given this diagram, and this is a 90-degree angle, what's an expression we could write for this length? If this vector is PQ, so the length of this side of the triangle, I'll write that in red, is the magnitude of PQ. D equals the magnitude of PQ times the cosine of theta. So looking at the relationship between PQ and N, what is this a part of? PQ dot N is, how can I write the dot product PQ dot N? Magnitude of PQ times the magnitude of N times the cosine of theta. So PQ cosine theta is PQ dot N divided by the magnitude of N. So our distance is given by the distance from this point to the plane, and I'm going to put an absolute value around our dot product because we want our distance to be positive. So, and we don't need two equal signs. Magnitude of PQ, magnitude of the dot product, or the absolute value of the dot product, we just want a positive distance, divided by the magnitude of N. So this is how we find the distance from a point to a plane using the dot product. Very similar to the way we found the distance from a point to a line. For the line, we used a cross product. For the plane, we used the dot product. We can also, sometimes you'll see it written as PQ, the magnitude of PQ times the cosine of theta is the magnitude of the vector projection of PQ onto N. So sometimes you'll see the distance related to the magnitude of the vector projection. I like thinking of it in terms of the dot product. It's a little more intuitive to me. So our distance from a point to a plane is given by this dot product. And the reason we use the dot product for a plane and the cross product for the line is for the plane we have a normal vector, and for the line we had a parallel vector. So we have vectors pointing in the different direction. So a nice compact way of finding the distance from a point to a plane. So let's look at an example, a couple of examples calculating with this idea, and then I have one other question that I wanted to ask you all, and then I want to expand on this a little bit. We can write this into a kind of a more complicated formula. I like this because it's nice and compact. It's there's not much to remember here, but we can expand it out and come up with a formula for the distance between the point from a point to a point. All right, questions? Questions so far? All right, so let's calculate a distance. So we need a distance from the point Q113. See if I can be a little better with my arithmetic here. To the plane (3x plus 2y plus 6z equals 6. So we need a couple of things to find our distance. We need a normal vector. So what is our normal vector going to be here? 3, 2, 6. Just pick out the coefficients on x, y, and z. So there's my normal vector. And I need a point on the plane. So I need my point P. How can I find a point on the plane?
Just plug in.
Plug it into the... So what are you saying we should do, Daniel?
Just solve the vector.
So you mean our equation? Yeah. So what would be an easy point to find?
0,
0,
0, 1.
0. So let's plug in 0. I usually do zeros for y and z, but I just plug in zeros for two of the components. So if y and z are 0, x has to equal 2. So 2 0 0 is on the plane. So I just plug in zeros for two of my components and solve for the third one, just like Daniel suggested. So there's our point on the plane. Just plug in zeros for two of the variables. So now I need my vector PQ. So I want to form PQ dot n. So the vector PQ is going to be what vector?
Oh, so just put in the vector and take P in the...
Right. So what's that vector going to be? And we want, so that would, yeah, we could do that. So 1, -1, 3. -3. So there's PQ. And our distance now is just going to be the absolute value of PQ dot n. So that's going to be the absolute value of 3 minus 2 minus 12 divided by the length of n, which is the square root of 9 plus 4 plus 36. Not 12. 3 times 6 is 18, yes. I'm having a rough time today. So we get this comes out to 17 over 7. So the distance from that point to that plane is 17/7 of a unit. 17/17. And the plane is kind of nice because dot products are much easier to calculate than cross products. Usually the arithmetic is easier. Today, not so much. All right, questions on that problem? I'm just trying to think what I was thinking of when I said 3 and 6 and ended up with 12.
It's okay, Mr.
Yeah.
One time I was so bad at calculus data.
One time?
Maybe more than one.
Maybe. When Miss Hine and I, when we work at Calc camp when we talked about solutions, and I make she makes fun of me for making mistakes like that. Don't you mean 18, right? All right. So I have a question for you, and then I want to talk about another distance problem. So let's say we have, our problem says we have a point A, 0, 0, 1, a point B, 2, 0, 0, and a point C, 0, 3, 0. And the problem asks us to find the equation of the plane containing A, B, C. So I don't want to go through the entire problem. I want to talk about how we would do it, what process we would use. We want the equation of the plane containing these points. So what pieces of information do we need to find our equation? What do we need and what do we have that's going to help us? Well, any of these three are going to give us a point on the plane, right? So that's some place to start. What other piece of information do we need for our equation? We need a normal vector. So how are we going to find a normal vector from these 3 points? Jacob says the cross product. So what are we going to form the cross product with? So we have 3 points. Can't we make a vector AB from 2 of those points? Wouldn't that vector be in the plane, since those 2 points are in the plane? And wouldn't the vector AC also be in the plane? If I form the cross product of those 2 vectors, what direction does the cross product point? Isn't it orthogonal to both of those vectors? If it's orthogonal to both of those vectors that are in the plane, isn't it going to be normal to the plane? So there's our normal vector. Our normal, and we could form the cross product of any combination of 2 vectors between the 2 points. So there's our normal vector. Any combination of those, and then any of these 3 could be our point, our P point on the line, and then we'd be set to write our equation. So our normal vector is given by the cross product that we can make from the vectors between 2 of these points. So you'll see problems like that will come up fairly regularly, where you have 3 points and you want to find the normal vector either to the vectors containing those points or to the plane. All right, I want to look at one last problem, and then we will be done. It's a problem where students often make a mistake.
Stop now, please.
We want the distance between x plus 2y plus 6z equals 1 and x plus 2y plus 6z equals 10. And I'm going to give you the distance between these parallel planes. And I'm going to say it is not 9. That's the mistake that students often make with this problem. It's not 9. So if I were to draw a side-on view of these 2 planes, What this is telling us is one is shifted 9 units in some particular direction from the other. So that distance will be 9. What we're looking for is that distance, which is not necessarily 9. So how are we going to solve this problem? So Jacob says, find a point in one of the planes. So we're going to find a point in one plane. Well, now our problem is reduced, just like we like to talk about, into one we've solved before. We just find a point in one of the planes, and we find the distance from that point to the other plane. We change it from a problem about 2 planes to a problem about a point in a plane. And we can find our normal vector. Since they're parallel, they share a normal vector, so we can find our normal vector easily. And then we can use our formula for the distance from a point to a plane. So I'm going to pick an easy point here. In this plane, let's find point Q. Put in x or y and z equals 0. So point Q is going to be 1, 0, 0. Point Q is in this first plane. And we need our vector PQ. So we find a point in this plane, so our point P. If I substitute y and z equals 0, I get the point 10, 0, 0. So my vector from P to Q, from this point to the point not on the plane, is, I'm going to write it as negative 9, 0, 0. I could use the one going the other direction as well, 9, 0, 0. Either one works. So this point came from this plane. This point came from that plane. Form the vector between them. My normal vector here is the vector 1, 2, 6. And now I'm set. So my distance is PQ dot in, which is just the absolute value negative 9 over the magnitude of my normal vector, which is 1 plus 4 plus 6 plus 36. And I get 9 over the square root of 41. So close to 9-ish, but it's not 9. All right, questions? All right, so let me, you might see this formula in some places. What we can do, for those of you that like formulas, I like the dot product, but we can come up with a distance formula for a point in a plane. I honestly, I never use it, but just want you to at least have seen it. So what we do for this formula is we start with our formula for the distance. So our distance is the absolute value PQ dot in. This is what we came up with, the one we've been using, over the magnitude of the normal vector. And we're going to apply it to a point. I'm going to call Q x0, y0, z0. So this is our point that's not on the plane. Our plane is ax plus by plus cz plus d equals 0. So that's our equation for our plane, and it contains the point P, x1, y1, z1. If we plug all of these values in, the value for the components of our normal vector, point Q is x0, y0, z0. Point P is x1, y1, z1, and write out the expression for this thing with all of these pieces put in, we can say that our distance is the absolute value of ax0 plus by0 plus cz0 plus d all over the square root of a squared plus b squared plus c squared. And d here is given by negative, like we said before, it's the combination of all the x1, y1, z1 pieces. So d is given by that expression. So for some people who like formulas that we can just plug things into, some people like this formula. So I just want you to have seen it. I never use it. I always just go straight to this. I find this very easy to calculate with, very intuitive as to what we're doing here. But you can expand it out and you get this. All right, questions? All right, so for part of your homework, I would like you to read. We know how to do that, right? On page 787 in your textbook, it gives a nice little tutorial about how to sketch planes in 3 dimensions. So read over that. We'll talk about it in class, but I don't want to go through an entire presentation about doing it. It's pretty straightforward. The book does a good job of explaining it. The book actually does have a lot of nice examples and words and explanations. So if you go to the book as a resource, it's kind of a nice thing. It's not only a source of homework problems. It's a pretty good calculus book. All right, and then the homework. I have to look here because I can't read my book. There you go.